Hello, Matt here from ChemistryStudent.com. In this video, we're going to look at metal aqua ion precipitation reactions. We're going to talk about what metal aqua ion precipitation reactions are, the acidic nature of transition metal aqua complex ions, and amphoteric compounds. Complex ions and ligand substitution have been covered in separate videos. Check the links in the description below. Before we talk in detail about precipitation reactions, there are a few essential ideas you need to be comfortable with. Transition metals are metals that can form one or more stable ions with a partially filled d subshell. In other words, ions of these metals always have at least one half-filled d orbital. Complex ions are made up of a central metal ion that is coordinately bonded to ligands. The overall charge of a complex ion is determined by the charge of the metal ion in it and the charges of the ligands bonded to it. Their formulas are written in square brackets. According to the Bronsted-Lowry definition, acids are proton, H+ ion, donors, and bases are proton, H+ ion, acceptors. In solution, acids lose a H+ ion that is accepted by a water molecule, forming H3O+, a hydroxonium ion. When we write H+ aqueous in equations, we are referring to H3O+ aqueous ions. Precipitates are solids that form rapidly in aqueous reactions. As they form very quickly, they don't have a chance to all join together and form one big solid. Instead, lots of small solid particles are produced. At first, this can make a solution look coloured. However, if left to settle, the precipitate solids will end up at the bottom of the solution due to their density. Recap done? Let's go. When aqueous sodium hydroxide or ammonia is added dropwise to solutions of transition metal aqua complex ions, coloured precipitates form. This is referred to as precipitation. The colour of the precipitate formed can be used to help identify the transition metal ion in the solution, as different transition metal ions can form different coloured precipitates. These have been outlined in revision sheets for specific exam boards at ChemistryStudent.com. Check the links in the description below. Some precipitates redissolve when excess sodium hydroxide is added, and some precipitates redissolve when excess ammonia is added, enabling further identification of the transition metal ion present. For example, when sodium hydroxide or ammonia is added dropwise to aqueous copper-2 ions, a light blue precipitate is formed from a blue solution. If excess ammonia is added, then the light blue precipitate redissolves and a deep blue solution is formed. The original precipitation formation occurs due to the acidic nature of transition metal aqua complex ions. When small quantities of hydroxide ions, OH-, are added to a solution of aqueous transition metal ions, their aqua complex ions effectively act as acids and donate a H+ ion, reacting with the added OH- ions. Each time this happens, the complex ion loses a H+ ion and its charge decreases by 1+. If it loses enough H+ ions, it will become uncharged and no longer able to remain dissolved in water. At this point, a solid precipitate gets formed. For example, with the copper-2 complex we just looked at, the CuH2O6 2+ ion reacts with two hydroxide ions to form CuH2O4 OH2. Two water molecules in the complex ion lose a H+ ion, meaning they become OH groups. As the complex ion had an original charge of 2+ and lost two H+ ions in the reaction, it ends up neutral and can no longer remain dissolved in solution, meaning it becomes a solid precipitate. These precipitation reactions actually happen in a couple of steps and due to an equilibrium that is established between the complex ion in solution and water molecules. Precipitation occurs because the added hydroxide ions affect this equilibrium and shift its position, forming the uncharged species and precipitate. When in water, transition metal aqua complex ions are weakly acidic, as the water ligands bonded to the central metal ion are highly polarized. This weakens their OH bonds, making them easy to break, meaning H+ ions can be easily lost. This polarization happens because the positive charge of the transition metal ion pulls electron density away from the oxygen atoms in the water ligands. Oxygen is a highly electronegative element, and as a result, if it loses electron density to the transition metal ion, it will try and regain some back by further pulling the electrons in the OH bonds towards itself, making these bonds highly polarized and weak. Free water molecules in the solution are able to come along and take a H+ ion from a water ligand and form a H3O+ ion, often just written as H+ aqueous. This leaves an OH group behind and decreases the positive charge of the complex ion by 1. We can show this as the complex ion losing a H+ aqueous ion. This is a reversible process, and there is an equilibrium established between the original complex ion, the new complex ion with a decreased positive charge, and a H+ aqueous ion. The same process can occur again with the new complex ion just formed, further decreasing its positive charge by 1 again. When the positive charge of the complex ion decreases to 0 overall, the complex ion has no overall charge and as a result is unable to remain dissolved in water. It goes from being aqueous to solid, and this is when the precipitate forms. For example, the aqua complex ion for iron 2, FeH2O6 2+, can lose a H+ ion to form FeH2O5 OH+, forming an equilibrium, and then the FeH2O5 OH+ can then lose another H+ ion to form FeH2O4 OH2, a solid precipitate. Again, this establishes another equilibrium in the solution. We no longer put square brackets around the species when it has no overall charge, as it is no longer an ion. And when writing out the formulas for these precipitates, sometimes the remaining H2O ligands are left out. For example, you will often see the FeH2O4 OH2 precipitate written as FeOH2, iron 2 hydroxide. Now, these transition metal aqua complex ions have a very low acidity, and this means the positions of these equilibriums we've just talked about lie very far to the left. Only a tiny proportion of their complex ions lose H+ ions in water, and as a result, no precipitates form. Adding hydroxide ions or ammonia molecules to their solutions, however, changes the positions of these equilibrium reactions, leading to the forming of solid precipitates. If hydroxide ions are added, they react with the H+ aqueous ions in the solution and form water molecules, H2O. This decreases the concentration of H+ ions in the equilibrium mixture and causes the position of the equilibrium for the first equilibrium reaction to shift to the right. For example, with the iron 2 complex, added hydroxide ions react with the H+ ions in the first equilibrium reaction, shifting the position of equilibrium, causing an increase in the concentration of FeH2O5 OH+ ions. The increasing concentration of these ions causes the position of equilibrium for the second reaction to shift to the right as well, causing an increase in the concentration of the FeH2O4 OH2 precipitate. It looks in the overall reaction like the added OH- ions have swapped places and been substituted with H2O ligands in the complex ions. This isn't the case, however. The original H2O ligands have simply lost a H+ ion, and the H+ ion has reacted with the OH- ions added. The same oxygens remain bonded to the transition metal ion in the complex the whole time. Adding ammonia dropwise causes the same effect as adding hydroxide ions dropwise. This is because ammonia is an alkali and reacts with water molecules in the solution to form ammonium and hydroxide ions. The hydroxide ions go on to affect the positions of equilibrium in the same way as if they'd just been added directly originally. Solutions of different metal aqua complex ions can have different acidities, depending on the charge and size of the metal ions present. Complex ions that have a metal ion with a 3+ charge have a greater acidity than complex ions with a metal ion that has a 2+ charge. This is because the greater the charge of the metal ion, or the higher its oxidation state, the greater the polarization of water ligands in the complex, meaning that OH bonds are weaker and easier to break, meaning it's easier to lose a H+ ion. As a result, for example, the iron-free aqua complex, hexaaqua iron 3, is more acidic than the iron-2 aqua complex, hexaaqua iron 2. Sometimes when excess hydroxide ions are added or a dilute acid is added, solid precipitates previously formed redissolve. Metal ion complexes that can do this are referred to as amphoteric. Amphoteric compounds are able to act as both an acid or base. Aluminium hydroxide and zinc hydroxide are both examples of amphoteric compounds. When formed from their aqua complex ions by the addition of dropwise hydroxide ions, the hydroxide precipitates formed can react with both an acid or base, redissolving with each. For example, if dilute hydrochloric acid is added to aluminium hydroxide precipitate, then the precipitate dissolves and aluminium chloride, AlCl3, is formed. If, however, excess hydroxide ions are added, another water ligand in the aluminium hydroxide precipitate loses a H+ ion and the ion AlOH4- gets formed, redissolving in solution. Aluminium hydroxide is able to react with both acids and bases then, making it amphoteric. So, to summarize, transition metal aqua complex ions form colored precipitates when aqueous sodium hydroxide or ammonia is added dropwise into solution. The color of precipitates formed can be used to identify the transition metal ion present in the solution. The precipitation reactions occur due to the acidic nature of a transition metal aqua complex ion. Water ligands in them are highly polarized, meaning H+ ions are weakly held by oxygen atoms in the water ligands and are easily lost. The positive charge of the transition metal ion in an aqua complex ion pulls electron density away from the oxygen atoms in the water ligands. Oxygen is highly electronegative, and as a result, if it loses electron density to the transition metal ion, it will try and regain some back by further pulling the electrons in the OH bond towards itself, making these bonds highly polarized and weak, meaning H+ aqueous ions can be easily lost by the complex ion. If this happens, an OH ligand group is left behind and the overall charge of the complex ion decreases by 1. A series of equilibrium reactions are established as the new complex ion formed is further able to lose H+ ions until its overall charge decreases to 0. At this point, the complex is no longer a charged ion and is unable to remain dissolved in solution, meaning it forms a precipitate. In a solution with just water, the positions of equilibrium lie very far to the left, meaning no precipitates actually form. However, adding hydroxide ions to such solutions affects the positions of these equilibrium reactions and causes more complex ions to lose H+ ions, and eventually precipitates form. The added hydroxide ions react with H+ ions in solution and form water molecules. This decreases the concentration of H+ ions in the equilibrium mixture and causes the position of equilibrium for the first equilibrium reaction to shift to the right, causing an increase in the concentration of MH2O5OH+ ions. The increase in concentration of these ions causes the position of equilibrium for the second reaction to also shift to the right, causing an increase in the concentration of precipitate for complex ions that had a 2+ charge originally. When writing the formula of hydroxide precipitates, sometimes the water ligands aren't included. Aqua complex ions in with metals that have an oxidation state of +3 have a greater acidity than complex ions with metals in that have an oxidation state of +2, as they cause a greater polarization of water ligands, making OH bonds weaker and easier to break. Aluminium and zinc hydroxides are amphoteric. If excess hydroxide ions are added to solutions with them in, their precipitates redissolve. Equally, if an acid is added, the precipitate will also redissolve. The precipitate is able to react with both an acid and a base, making it amphoteric. I hope you found this video useful. Please check out other relevant videos in the links given in the description below and visit chemistrystudent.com for free notes and revision materials.